Hello, welcome to the midterm demo for the Optical Beacon Tracker for Optical Wireless Communication by Group 4, sponsored by the Night Vision Lab. 4 is comprised of Seth Johnson, the Photonic Science Engineer, Raymond Lotus, the Electrical Engineer, Blake Baez, the Computer Engineer, and has community reviewers Dr. Kyle Renshaw, Mark Maddox, and Justin Phelps. Our overall project will consist of a receiver and beacon, and in this video we're going to demonstrate the functionality of our beacon system and the photodetectors of the receiver. And these are the specifications for the project. The specifications highlighted in orange are the specifications we will be demonstrating in this video.
Here we will demonstrate the IMU chip and its functionality and its subsystem. And here on the Arduino IDE, we can see the output of the XYZ parameters in the compass direction. Here it is facing north, as we can see by the phone compass. We cannot keep it too close because of interference. And I will spin it around. Facing southeast or south-southeast. Here is facing east-northeast. And to showcase the other parameters for the Y and Z, here is the GPS module, along with the antenna, the GPS chip, and its function. SD2 via UART. Here on the Arduino IDE serial monitor, we are outputting the amount of detected satellites, longitude, the latitude, the speed, and the altitude. Here, for verification, we have the coordinates. Here are our VTech 35 kilogram digital servo motors put together to make a gimbal mount. As you can see, this is connected to the Arduino Uno. Sadly, every single one of our microcontrollers have died, as well as our other motors. These are the only parts we have left demonstratable until we can order new ones. Here's it running random commands just for demonstration. However, we do have the transmitter tracking working perfectly wireless, but as stated before, when working with the ESP32 earlier, the chip sadly got too hot and died.
Here we were going to demonstrate the optics of our beacon. The components are the fiber output expander, the dichroic mirror, the diffuser plate, the 850 nanometer LED array, our LED array collimator, and our beacon output expander. The rig was constructed based off of the diagram on the right, and in this we are now going to show the specification for beacon output divergence. To measure the divergence of our beam, we have our LED array powered via power supply, the output of a fiber laser, our beacon rig prototype, 2 rulers, and 2 infrared cars that are sensitive to 850 and 1550 nanometers. Here we can take a note of how our target is at 20 centimeter mark, and our 2 IR cards are approximately 60 millimeters apart. The reason for this is that once we turn off our broadband light source, you can vaguely see the outline of our beacon spot size and how our infrared cars are just outside of said spot.
Here we have our quad cell photodiode hooked to our differential amplifiers. Our X and Y coordinates are provided here on the multimeters. As you can see, when I cover my hand over the lens, we receive no signal. But when light hits the quad cell, we are able to determine X and Y coordinates for positioning of our receiver.
By taking our measured values and using 2 times the arctangent of our final diameter and our first diameter, and then 2 times the distance between them, being 130 millimeters, 60 millimeters, and 100 millimeters respectively, we get a divergence angle of 38.58 degrees, which is just underneath our desired specification, which means there's still more work to be done on the optical beacon. We'll show the outputs of our quadrant photo detector.
Here we have our quad cell photodiode hooked to our differential amplifiers. Our X and Y coordinates are provided here on the multimeters. As you can see, when I cover my hand over the lens, we receive no signal. But when light hits the quad cell, we are able to determine X and Y coordinates for positioning of our receiver. As I rotate the lens, you can see that the X and Y coordinates change.
Here, we can demonstrate the weight of our beacon and receiver systems. On the left, you can see that our beacon weighs less than 1 kilogram, which leaves us with over 4 kilograms of weight that could be added in the future. On the right is our receiver, which is mostly taken up by our gimbal, the Grimsey, which has not been demonstrated in this video. It currently weighs 1.8 kilograms, which means we can add 3.2 kilograms to the receiver. What's left to do is acquire and assemble our second batch of PCBs, acquire our driver for our portable laser diode, control the receiver gimbal with the speed and accuracy listed in our specification table, and then fully assemble the beacon and the receiver. This concludes the midterm demo for Group 4. Thank you.